Alrighty, so we're going to go ahead and get started. Welcome to the multispectral and hyperspectral imaging in security with our speaker, Jonathan Hackney. Go ahead, Jonathan, to the next slide. Just as a quick introduction, Jonathan has a history of working in the industrial automation industry. He enjoys talking and learning about technological advancements, especially machine vision and SWIR imaging. As for us, Computar has a history of over 40 years in innovative optics, using Japanese engineering and global agile production facilities. On to you, Jonathan.
Good morning, everyone. In this webinar, we're going to talk about multispectral and hyperspectral imaging and security. First, we're going to start with an introduction into the multi and hyperspectral realm. And next, we're going to go over the differences between the two. Then we're going to talk about different applications of multispectral and hyperspectral imaging and security. After that, we'll go over some case studies. We're going to talk about some challenges and limitations, and then we're going to state some conclusions and talk about some solutions. And finally, we're going to have a Q&A. So first, let's start with the introduction. So multispectral and hyperspectral imaging are advanced technologies that have found various applications in various fields, including security. These technologies are used to capture and analyze images of objects or scenes using multiple spectrum bands or wavelengths of light. So let's start with multispectral imaging. So multispectral imaging is a technique used to capture and analyze images at multiple wavelengths or bands of the electromagnetic spectrum. It involves the use of specialized cameras or sensors that can detect light beyond the visible spectrum, such as infrared or ultraviolet light. By capturing images at different wavelengths, multispectral imaging can reveal hidden details and patterns that are not visible to the naked eye. This technology is used in various fields, including remote sensing, medical imaging, and art conservation. In security, multispectral imaging is used to detect hidden objects such as weapons, explosives, or drugs by analyzing the object's spectral signature. So how does multispectral imaging work? Multispectral imaging typically uses 3 to 10 spectral bands to capture images of objects or scenes. The captured images are then analyzed to extract information about the object or scene, such as its color, texture, and composition. Multispectral imaging is like hyperspectral imaging, but instead of acquiring many continuous narrow bands of wavelength information, it acquires a smaller number of broader wavelength bands. In multispectral imaging, the scene is typically imaged using a camera or sensor with filters designed to capture light in specific wavelengths. These filters may be mounted in front of the camera or integrated into the sensor. The multispectral image cube of a pork chop is illustrated with various shortwave IR LED wavelength bands. And this image is a courtesy of smart vision lights. So as you can see, as we move through the different wavelengths bands of say 1050, 1250, 450, and 1550 nanometers, certain parts of the image change, allowing us to see more details that we couldn't otherwise see. The resulting images are then processed to extract information about the spectral properties of the scene. This may include creating false color images where different wavelength bands are assigned different colors, or using algorithms to extract different features or information from the image. Multispectral imaging is often used in remote sensing applications, such as satellite imaging, where it can be used to monitor changes in vegetation, water quantity, and other environmental factors. It is also used in medical imaging, where it can be used to highlight specific tissues or structures based on their spectral properties. It provides a way to capture and analyze information about the spectral properties of a scene and has a wide range of applications in science, defense, industry, and medicine. So let's switch to hyperspectral imaging. So hyperspectral imaging, or HSI, is typically defined as spectral sensing technique that takes hundreds of continuous narrow wave bands images in a visible and infrared regions of the electromagnetic spectrum. So this is how hyperspectral imaging works. So the hyperspectral cube is created by acquiring multiple images of a scene, each at a different wavelength. The resulting data is then processed to extract spectral information for each pixel in the scene. This data is often represented as a spectral signature, which is a plot of the reflectance or radiance of the scene at each wavelength. HSI can detect and differentiate between subtle differences in the spectral signatures of different materials, allowing for identifying, classifying objects in the scene. This makes HSI useful in a variety of applications, including remote sensing, environmental monitoring, and medical imaging. To acquire hyperspectral data, specialized sensors are used to capture images at very narrow wavelength bands. These sensors often use a technique called push broom imaging, where the sensor is moved across the scene while continuously acquiring data. Once the hyperspectral cube is created, various processing techniques can be applied to extract information from the data. These techniques may include spectral unmixing, where the contributions of different materials to each picture are estimated, or classification, where the spectral signatures of different materials are used to classify pixels into different categories. So let's get into some history. Although HSI was originally developed for mining and geology applications, its usage has quickly spread into other civilian sectors, and more recently into the military sector due to the ability to differentiate between materials. In military and security applications, the technique has been significantly adopted for the detection and recognition of targets that are normally well camouflaged with its background and surrounding environments. Hence, HSI is designed as a countermeasure, allowing lookalike targets to be acquired. So now let's dive into some applications of multispectral and hyperspectral imaging and security. So the first would be border control and enhanced detection capability. So remote sensing can be used for remote sensing to detect, monitor various security threats such as illegal mining, deforestation, and land use changes. Air and marine officers use surveillance planes equipped with undermounted infrared cameras to identify and follow up on anomalies picked up by radar. US Customs and Border Patrol, or CBP, has used large and small drones for border monitoring in remote areas of land and even the sea. Low light or night vision imaging, SWIR cameras can operate down to starlight conditions, receiving adequate illumination from the weak natural phenomenon known as atmospheric night glow. Hydroxyl ion emissions create night glow in the shortwave infrared portion of the spectrum. And then the other is landmine detection. Hyperspectral and multispectral imaging have also gained popularity for their ability to detect landmines. Both techniques use remote sensing to analyze the reflection and absorption of light from a target area, which can reveal the presence of hidden landmines. Hyperspectral imaging can detect the unique spectral signatures of landmines, which differ from those of surrounding soil and vegetation. By analyzing these signatures, experts can identify the exact location of landmines and create maps of minefields. Multispectral imaging uses several wavelengths of light to create images of a target area by comparing images taken at different wavelengths. Experts can identify areas where the reflection of or absorption of light is different, indicating the presence of landmines. Both hyperspectral and multispectral imaging can be used by unmanned aerial vehicles, or UAVs, commonly known as drones, allowing experts to cover large areas quickly and safely. This is especially useful in areas where landmines are a severe threat and ground surveys are not feasible. So some other applications for MSI and HSI are biometrics and recognition of persons. Whereas long and medium shortwave infrared sensors can spot targets based solely on their heat emission, SWIR cameras and sensors can see reflected light in the shorter wavelengths just beyond the visible range. As a result, the images are close representations of what is seen in the visible spectrum. Humans are very recognizable, with the typical difference being that all hair shows white due to the lack of moisture in hair. Conversely, skin shows darker due to its high moisture content. Long and medium wave sensors provide detection, while SWIR and visible sensors provide recognition. The beauty of SWIR is that recognition can be achieved covertly in darkness. In the case of biometric identification systems, multispectral and hyperspectral imaging lenses capture and analyze these images of fingerprints, irises, and other biometric features. These systems use the spectral properties of the images to identify unique features and match them to store data to verify identity. One of the unique aspects of SWIR imaging is the unusual way in which natural and artificial materials appear in the SWIR part of the spectrum. For example, hair is highly reflective and thus appears white in the black and white imagery seen in the SWIR part of the spectrum. Wavelengths from 0.7 microns to 2 microns. Artificial hair, on the other hand, will appear much darker, sometimes almost black. In the image seen here, an actor is wearing typical stage makeup in the color image at the left. On the right, however, we see the same actor in the SWIR band. Now, the artificial elements of the makeup appear obvious. Translating this to a border crossing or checkpoint situation, can now assume that anyone wearing a disguise as they approach the border has some form of criminal or even hostile intent. SWIR imaging can add a very valuable layer of protection to the defense of the homeland. Now let's talk about some application systems such as airport security scanners. Airport security scanners detect potential threats in luggage and cargo using multispectral and hyperspectral imaging lenses. Analyzing the image's spectral properties can identify weapons, explosives, and other dangerous items. Another example is chemical detection systems. So multispectral and hyperspectral imaging lenses are used to identify and analyze the spectral properties of chemicals and other substances. These systems may be used in security applications to detect the presence of potential chemical threats, such as explosives or hazardous materials. Some additional applications are improved identification and classification of objects, whether it's concealed explosives or weapons, increased accuracy and efficiency in surveillance. Another example are illegal drug production facilities. And in the case of forensic analysis, hyperspectral and multispectral lenses can be used for forensic investigation to detect, analyze trace evidence, such as fingerprints, fibers, and DNA, which can help solve crimes. So let's talk about some case studies. Example of successful implementation of multispectral and hyperspectral imaging in security. There was a study by multiple PhD professors in computer science at the Indian Institute of Technology in Hyderabad, and they considered face recognition under different environments, introspectral and cross-spectral problems. They tested different infrared bands against visible face images to evaluate the performance. They also verified different environmental conditions and distances of the different bands of infrared. An accuracy of 100% was obtained with visible image versus the SWIR of the IR band. This was done under a controlled environmental condition with a 30-meter distance. In contrast to visible spectrum, infrared may extract external and vital internal anatomical data, such as faces' vascular systems. Data collected with infrared cameras offer significant benefits over those collected with visible spectrum cameras for face identification. So now, what are the challenges and limitations? So technical limitations of spectral and hyperspectral imaging are, number one, cost. These imaging systems are expensive to purchase and maintain, which makes them less accessible to smaller organizations. Next is the complexity. Multispectral and hyperspectral imaging systems require specialized knowledge and expertise to operate and interpret the data, which can be a barrier for some users. Another challenge is limited field of view. Most of these systems typically have a narrow field of view, which can make it difficult to capture a wide area or even track moving targets. Luckily, our FOVs have a very wide range to fit several applications. And lastly, environmental factors. The accuracy and effectiveness of these systems can be affected by weather conditions, lighting, and atmospheric interference. So now, what are some solutions to these challenges? So for cost, you need competitive pricing. Computar can offer very competitive pricing for our ViSWIR Light lens series and our Hyper APO lens series, helping the end user reduce overall cost for MSI and HSI systems. For complexity, you need user and installer friendly solutions. Computar can offer our specialized knowledge and expertise here in America with the help of our optical engineers based in Japan. For limited field of view, Computar can offer a wide field of view with our ViSWIR lens that can achieve a diagonal field of view of up to 78 degrees. And finally, for environmental factor limitations, Computar can offer environmental enclosures, including explosion-proof enclosure solutions manufactured by our sister company, BSI or Broadsight Systems. So some recommendations. Let's talk about Computar's ViSWIR series. A high-quality lens like ViSWIR series can help capture more precise and detailed information in different spectral bands, leading to better analysis and interpretation of data. The ViSWIR series minimizes the focus shift within a few microns at a wide range of wavelengths by using ultra-low and low partial dispersion glass paired with superior design technology. With this, spectral imaging is achieved with a single camera solution by simply enhancing the lighting. With our ViSWIR Hyper APO series, there is no focus shift at any wavelength. Instead, the lens adopts an Hyper APO floating design, reducing the focus shift at any wavelength and working distance. This function makes the series ideal for multiple applications, including machine vision, UAVs, and remote sensing. By selecting a superior lens that meets your needs, you can assure that your imaging data is as accurate and informative as possible. So we have some other recommendations here. First, the MPT series. This series is one of our highest megapixel lens at 45 megapixel. It is a fixed focal C-mounted lens and is suited for 4/3 inch or 1.4 inch image sensors. Next, we have the MPY series. This series is extremely lightweight, high resolution, fixed focal C-mount lens that pairs with a 1.1 inch sensor. And finally, the MPZ series. This series is very compact with a 20 megapixel capability, C-mounted lens, and it's suited for your 1 inch image sensors. All right, so some conclusions. So I'll start off with a quote from Photonics. The beauty of SWIR is that recognition can be achieved covertly in darkness. Hyperspectral and multispectral imaging are powerful tools for security applications, but with continued research and development, these techniques may become even more effective and widely used to make the world safer. As research and development in the hyperspectral and multispectral imaging continue, these technologies are likely to become even more effective and widely used in various security applications. This would result in improved safety and security for individuals and organizations and entire countries. And then finally, we're going to have a Q&A. So if you guys have any questions, you can feel free to put them in the chat or even ask me. We should be able to answer any kind of questions you guys have.
If you all are feeling shy as well, you can feel free to do a direct message to Computar Optics right there in the chat. Otherwise, you can go ahead and shoot your questions in the main chat. We'll go ahead and start off. Let's see, we've got, do you need to adjust focus for different wavelengths?
Well, for the SWIR, no. For the Hyper APO series, you actually have zero focus shift or zero need for focus shift. On our ViSWIR light series, it's only by a few microns. It's only slightly, but the Hyper APO has a much better transmissibility of the light. So there's really no need for focus shift on that SWIR.
And the non-SWIR lenses, but what about the SWIR ones?
Yeah, so we have basically two major series that we have in our SWIR. One is our SWIR Light. It's kind of like a Coors Light, if you will. But that sensor size covers a 2/3 inch and a 1/2 inch, and with a resolution of 1.5. And within that SWIR light series, we have a 5 millimeter all the way up to a 50 millimeter fixed focal on those guys. For the Hyper APO series, which is the next step up, which is it's almost like diesel, you know. The Hyper APO series, it's a 2/3 inch sensor, but it's a 5 megapixel resolution. And we cover from 8 millimeter all the way up to 50 millimeter on that guy.
Do your SWIR lenses operate in?
So the wavelengths for the SWIR operate in 400 nanometers to 1700 nanometers. So it's going to cover your visible all the way up to that shortwave infrared.
Focal lenses for your SWIR series?
So so the fixed focal is the ones that we market. Now we do have a basically made to order product. It's our ViSWIR Zoom series. So that's a 1/1.8 inch. The resolution is 1.3 megapixel. And that guy, you can actually look for that guy on YouTube. They've got a couple of really cool videos. But that guy has over a 1300 millimeter focal length. It's actually really cool lens. You can see objects over 30 kilometers away in the SWIR band. So really cool stuff, especially with that guy. But if you do have a need for that, definitely let us know. It's a made to order product.
Any other questions? You can go ahead to the contact page so everybody knows how to contact you, Jonathan.
Yeah, sure. This is our sources. And then this is a QR code that you can get my contact information directly. My email is jhackney@cbcamerica.com. And my personal phone number, it's 919-414-8098.
This recording and this presentation probably later today, this afternoon. And like I said, if you have any more questions, feel free to reach out to Jonathan here. Thank you all for joining us and have a wonderful rest of your day and weekend.